Now we are going to explore the application of various statistical tools on the performance measurement of networks. Specifically, we'll see what are MM1 systems as basic instance of queuing models. Then we'll find out what is the arrival as an event, how can it be modeled as a Poisson process, and how can we visualize it as a graphical form of distribution. The reference is Dimitri, Bertsikas, and Gallagher. So what are MM1 systems? M/M/1 are queuing systems which consist of a single queue. Single queue means that the number of users would be asked to be serviced in a one-by-one manner, and they'll be held up in a single queue. This could be a single server, a single computer, a single queue of a router. In terms of communications, it could be a single transmission line. Here, one refers to single, and the first two M's refer to more information, as we shall see. The arrival is expected to be Poisson, and the service is going to be exponential, with the mean 1 upon mu represented in seconds. So what is Poisson? What is exponential? We shall explore it as we proceed. Let's look at the arrivals first. Arrival means the coming of customers or the reception of packets at the input queue of a router. The arrivals are Poisson process based. We can represent arrival as AT, which counts the number of packets. It is going to determine the total number of arrivals which happen from 0 to a time instance t. It means we are interested in the total number of arrivals that were counted in a time interval. Poisson process is actually a very good way of looking at the arrivals. It looks at the aggregate traffic as a measurable quantity where the arrival follows a unique pattern, that is, the arrivals are similar, that is, the packets which arrive are of the same kind almost, and their arrivals are totally independent of each other. It means the first incoming packet does not influence the coming or the arrival of the second packet, and so forth. Poisson process, which is mathematically representable, allows us to break down the aggregate traffic at the input of a router as merged n independent and identically distributed arrival processes. These are also known as IIDs. Each process is broken down into lambda divided by n, which means whatever the arrival may be, whatever the total count may be, it is actually dependent upon n customers generating data. So the total lambda as the arrival rate could be represented as a fraction or lambda divided by n. So of course, if each user is transmitting its own packet flow, so if we multiply lambda divided by n as the average data generated by each user, and if we know the total number of users which are generating this data is n, so again we get lambda. So this is a kind of easy manipulation or an easy form of understanding Poisson process. As I said earlier, the arrivals are occurring independent and in disjoint time intervals. That means the timeline that we are looking at is so minute or is divided into such small time instances that at any one time instance there is an arrival, and this arrival is not coinciding with any other arrival. So you could always ask, how is it possible? Because two packets could arrive at the same time. Well, two packets can arrive at the same time, but there would be some kind of time differential between the two if we are able to zoom in on the time scale. The number of arrivals in any interval of length tau, say we are interested in measuring how many packets have arrived in this interval tau, it is represented by the expression you see here, that probability of arrival in t plus tau minus the arrival in t interval is equal to n number of packets, which is given by Poisson distribution. The Poisson distribution has three well-known parts. The first one is the exponent, e to the power minus lambda t, lambda tau. The second expression is lambda tau to the power n. And the third expression in the denominator is n factorial. So what you see here is that the number of packets which are arriving are going to follow a graphically decaying exponential starting off from the peak, and you can also look at it as a shifted or skewed normal distribution. Here you can see that the arrival at any input of a system follows these curves. You can look at the values starting from lambda is equal to 1 through up to 9. And you see that smaller the value of lambda, that is smaller the value of the arrival, it is quite skewed. It's very much different from the normal distribution. But as the number of arrivals increase, it starts behaving like a normal Gaussian system. And that is what we understand, that for very large arrivals, it would start behaving like a well-known normal Gaussian system or a normal distribution.